Hello and welcome back. In this video we're going to review how to find vertical asymptotes and horizontal asymptotes. Recall that vertical asymptotes you can find by taking the limit as x approaches an x value, either from the left or the right side. And if you get either positive infinity or negative infinity coming in from the right or from the left, then you've got a vertical asymptote there. X equals whatever that x value is. We'll call that a. Now for rational functions, this is going to happen when the bottom of the rational function is 0 and the top of the rational function is not 0. And just to remember, rational functions just mean a polynomial over a polynomial. So when the bottom polynomial is 0 and the top polynomial is not 0, then you've got a rational function. What this means is when you do take the limit, the bottom is going to shrink down to 0, the top is going to approach a non-zero number, and so overall that's going to approach either positive or negative infinity as you're coming in from the left or the right. In the first example, we're asked to find the vertical asymptotes of f of x equals x cubed over x to the fourth minus 16. So the key here is going to be to look at where the bottom of the polynomial is equal to 0. We're going to need to factor, and we'll get x squared, that was a funny looking 2, x squared minus 4, and then x squared plus 4, that's the difference of squares. Then we can factor the x squared minus 4 as another difference of squares, as x minus 2 and x plus 2. Now the x squared plus 4 we can't factor anymore because that's an irreducible quadratic. So we only get two x values that solve this. And those two will turn out to be our vertical asymptotes. X equals 2 and x equals negative 2 are vertical asymptotes. The only thing we have to do to make sure of that is to note that when we plug in those x values into the top of the fraction, we get a non-zero number. So definitely we have vertical asymptotes. You just want to confirm that the top is non-zero. If both the top and the bottom are 0, well then you have an indeterminate form. And there it's possible that it's a vertical asymptote, but it's possible it's not a vertical asymptote as well. There. It could just be a hole in the graph. For the next example, we're going to look at, does f of x equal x ln x have a vertical asymptote at x equals 0? Well, it's a good question to ask because ln x has a vertical asymptote at x equals 0. If you remember the graph of ln, I'll just draw a quick picture of the graph of ln. It looks something like this. There's a vertical asymptote that just strayed. Vertical asymptote at x equals 0. And I should mention too that x equals 0 would be the equation for that vertical asymptote, just like x equals 2 is the equation for that line, that vertical line. And then x equals negative 2 is the equation for that other vertical line, that other vertical asymptote. Okay, but back to x ln x. So to find out if we have a vertical asymptote at x equals 0, we can check by taking the limit as x approaches 0. Wow, there's like some drag racing going on. I don't know if you can hear that. Yes. Okay. It's too bad I don't edit these things out. Man, they're really going at it out there. Okay, so if we think about taking the limit as x approaches 0, well, we could approach from the left or the right-hand side. But the thing is, if we're approaching from the left side, natural log is going to be undefined. So this function is not defined if x is approaching 0 from the left side. So we can really only approach 0 from the right side. So let's take the limit as x approaches 0 from the right side of x ln x. What we have here is an indeterminate form of type 0 times negative infinity. So why is that? Well, as x approaches 0 from the right, this x factor is going to 0. And as x approaches 0 from the right, ln x is approaching negative infinity. You can see that from the graph. ln x is going down to negative infinity as x approaches 0 from the right. So these kind of indeterminate forms, 0 times infinity, we looked at in packet 13, L'Hopital's rule. And we saw that we can take a limit like this, flip one of its factors down to the bottom. I'm going to take the x and flip it down as a 1 over x. Then it turns into a, in this case, negative infinity over positive infinity kind of limit. Infinity over infinity, the negative signs don't matter. It's basically an infinity over infinity, which you can use L'Hopital's rule on. We're going to apply L'Hopital. Which means we're going to take the derivative of the top, the derivative of the bottom. Now, if we look at that limit, it's again like an infinity over infinity type limit. It's actually infinity over negative infinity. But we're not going to use L'Hopital a second time because let's try to simplify first. It's always good to look to see if you can simplify. Good life advice. Simplify, simplify, simplify. When we simplify, dividing by this fraction is like multiplying by the reciprocal. So you're going to get an x squared over an x, which gives you just x, and then the positive divided by negative gives you the negative. Now when we plug in the 0, we just get 0, well, negative 0, which is 0. So we got the limit as x approaches 0 from the right of x ln x is equal to 0. What does that say? To answer the question, do we have a vertical asymptote at x equals 0? If you said no, that's correct, because we didn't get plus or minus infinity. We didn't get a positive infinity or a negative infinity here, so there is no vertical asymptote at x equals 0. The graph, instead, is just heading to a y value of 0. As x approaches 0 from the right, the y values are getting closer to 0. They're not blowing up to infinity or negative infinity. So no vertical asymptote at x equals 0. Let's move on to horizontal asymptotes. Recall that to find horizontal asymptotes, we can take the limit as x approaches positive infinity, so moving to the right, or negative infinity, moving to the left. And if we get a number, a fixed number, then that means we have a horizontal asymptote. Y equals that number. I forgot I had chopsticks. So that means that the graph, as x, let's say as x approaches positive infinity, the y values are getting closer to that number. That means the graph is getting closer and closer to that horizontal line. Thus, a horizontal asymptote. Now for rational functions, p of x over q of x, so a polynomial over a polynomial, we have a shortcut that we can use, and that's by looking at the degrees of the top and the bottom. Basically, if the degree of the top is less than the degree of the bottom, you're going to have a horizontal asymptote y equals 0. And that's because the bottom, because it has a higher degree, is going to get larger faster than the top, and that'll drag the whole fraction down to 0 as x approaches either positive or negative infinity. So you'll get a horizontal asymptote y equals 0. If the degrees are equal on top and bottom, then the horizontal asymptote will be y equals the leading coefficient of the top over the leading coefficient of the bottom. There, if the degrees are equal, they're both getting bigger at the same rate, and so you divide their leading coefficients to find the y value that is being approached. And then if the degree of the top is bigger than the degree of the bottom, well then you don't have a horizontal asymptote at all. In this case, you might have a slant asymptote or possibly a higher degree like a parabolic asymptote, but the most you'll want to worry about is slant asymptotes. So the example says find the horizontal asymptote of f of x equals 5x squared over 3x squared plus 7. There, if you look at the degrees, you've got a degree of 2 on the top, a degree of 2 on the bottom, so the degrees are equal. So that's the second case. We're going to divide the leading coefficients to figure out what the horizontal asymptote is. Looks like it's y equals 5 over 3. Now for the second example, the horizontal asymptote of f of x equals x cubed times e to the negative x, we can't use our shortcut because that's not a rational function. It's not a polynomial over a polynomial. So in this case, what we'll do is we'll take the limit. Let's start with x going to positive infinity. Now we have to check both directions if we have a non-rational function. We got to check both directions to see if we have horizontal asymptotes. It's possible for a non-rational function to have more than one horizontal asymptote. The most it could have would be 2, one going to positive infinity, one going to negative infinity. Or it could have 1, and all the rational functions as well are only going to at most have one horizontal asymptote, or it could have no horizontal asymptotes. Of course, this would be a terrible example if it had no horizontal asymptotes, so it's probably going to have at least one. So let's take the limit as x approaches positive infinity of x cubed e to the negative x. Now if we look at the type of that limit, let me do it over here. If we look at the type of the limit, the x cubed is going to infinity as x goes to infinity, and the e to the negative x is approaching 0 as x approaches infinity. Just to remember what e to the x looks like, remember e to the x looks like this, and it has a horizontal asymptote y equals 0. So as x approaches positive infinity, negative x approaches negative infinity, and e to the negative infinity is going to approach 0. So we have an infinity times 0, which is an indeterminate form. Now we're going to use our same trick about taking one of those factors and bringing it down to the bottom, and that negative exponent is just begging to be brought down to the bottom anyway, so the e to the negative x will bring that down to the bottom as an e to the x. And now what we're set up for is a type infinity over infinity, which we can use L'Hopital on. I'm just going to write loop. We'll take derivative of top and bottom. We've got 3x squared over e to the x. Check to see what kind of a limit we have. Looks like infinity over infinity again. So we're going to use another L'Hopital. So here we're going to get limit as x approaches infinity of derivative of top is 6x, derivative of bottom is e to the x, and checking our type, another infinity over infinity. So we got another L'Hopital. So let me check my time. Okay, limit as x approaches infinity of 6 over e to the x. And another wait, almost lulled us into a L'Hopital loop. Alright, this one is not an infinity over an infinity. This one is 6 over infinity as x approaches infinity. So this is going to drag the fraction down to 0, right? The top is staying at a fixed 6, and the bottom is blowing up to infinity. So this is being dragged down to 0. It's easy to get in this L'Hopital trance where you're just taking L'Hopital, 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 and then forget what you're doing. But remember, each step of the journey, you want to check again, what type of limit is this? And then if it's infinity over infinity or 0 over 0, you can use L'Hopital. And then always, after you use a L'Hopital step, make sure you simplify first. All right, now, do we have a horizontal asymptote? The answer is yes, we do. We have a horizontal asymptote y equals 0. So this is the y value that the function is approaching as x approaches positive infinity, and therefore we have a horizontal asymptote y equals 0. Now, that was only as x approached positive infinity. You also have to think about x approaching negative infinity. Limit as x approaches negative infinity of x cubed e to the negative x. Let me make that a little bit more clear. X approaches negative infinity. Now in this case, the x cubed is approaching negative infinity, right? Large negative numbers, when you cube them, are large negative numbers, even larger. And if you plug in a large negative number into e to the negative x, you get the negatives cancel to give you positive large number, and e to positive large numbers go to positive large numbers. So e to the negative x will go to positive infinity as well. And an infinity times an infinity is going to be an infinity. In fact, this is going to negative infinity. So no horizontal asymptote when x approaches negative infinity. As x goes to the left, the graph is just going down to negative infinity. The y values are going down to negative infinity. So no horizontal asymptote in this direction. But it's good to check. So that's vertical and horizontal asymptotes. In the next video, we're going to have our final battle with graphing using calculus. Please join us for the next video. Thanks for watching, and see you next time.